For more than 20 centuries, the moon has been studied and investigated by skilled and ingenious men. They have come to realize that in comparing the moon with the Earth, we can learn more about the history of both, and ultimately, more about the history of the solar system as a whole. In the process, we would gain a new perspective about our own place and role on our small blue planet. Before manned Apollo flights to the moon, we could only study it remotely, primarily by way of instruments such as the telescope. And recently in history, by way of automated spacecraft. Early in the 17th century, Galileo Galilei became the first of the great scientists to use the telescope, a quite novel instrument at the time, to study the moon.
I feel sure that the surface of the moon is not perfectly smooth, free from inequalities and exactly spherical, as a large school of philosophers considers. On the contrary, it is full of inequalities, uneven, full of hollows and protuberances, just like the surface of the Earth itself.
His discoveries helped overturn erroneous beliefs popularly held and taught for 14 centuries and laid the foundation for modern lunar science. Galileo would be followed by a stream of other scientists and a mass of new information and knowledge. The centuries of investigations produced a great deal of information about the moon. For instance, the moon, orbiting once about every 4 weeks, always keeping the same face toward Earth, is far larger and more distant compared with its planet than are any of the other moons of our solar system compared with their planets. In fact, the moon is often considered a planet in its own right. Further, some scientists believe that the moon is gradually pulling away from the Earth, which in turn is gradually revolving slower and slower on its axis. There is at least some evidence that the moon was much nearer Earth in the past, although no one knows just how near it might have been. The surface of the moon has aptly been described as a cosmic battlefield, a place terribly hostile to life. It is alternately baked and frozen, in temperatures ranging from some 250 degrees Fahrenheit above zero to some 250 degrees below zero, and it is seared by radiation from the sun. As a whole, the surface of the moon may be divided into the heavily cratered highlands, which Galileo called the brighter parts, and the Maria, which Galileo called the darker parts. The highlands are far more rugged, having 20 to 30 times more craters than the Maria. This means that the formation of craters had slowed drastically by the time the Maria basins were filled. In essence, the highlands were formed when the moon was a growing, dynamic body, the Maria when the moon was far less active. In contrast with the moon's face, the far side is almost totally covered with highlands. There simply are none of the great Maria. Telescopes and automated satellites brought us close-up looks at many individual features. For instance, in the highlands, craters which look much like certain volcanoes on Earth. Other craters which look like impact sites, sometimes with streaks of debris radiating hundreds of miles away from their centers. Mountain ranges which tower thousands of feet above the surrounding plains. Symmetrical hills known as domes. Apparent red glows, first seen in the 1950s. Where the highlands and Maria meet, there are features which look much like ocean waves approaching a rugged shoreline. The Maria basins are comparatively smooth and flat, likened to a frozen sea by the first men to orbit the moon. And they are marked by so-called wrinkle ridges, which have the appearance of frozen waves. phantom craters, evidently real craters virtually inundated by Maria materials. Then there are valleys which wander for hundreds of miles across the surface. Great fractures or faults which may slice across the moon's face for 100 miles. There are the newly discovered mass concentrations, or mass cons, buried beneath the circular Maria, and their gravitational attraction actually distorts the flight paths of space vehicles circling the moon. From Surveyor spacecraft, there was even some knowledge of the nature of the soil and the chemistry of materials. Yet for all we had learned, for all we had discovered, even with unmanned space vehicles which landed on the surface, and manned Apollo vehicles which orbited above the surface, the moon still somehow seemed remote and inaccessible. Until that day in July 1969.
Forward. Forward. At 40 feet down, 2.5. 30 feet, 2.5 down. Straight shadow. 4 forward. 4 forward. Drift into the right a little. 20, down a half. 30 seconds forward. Just picking up some dust. Got the shadow out there. Contact light. Okay, engine stop. We copy you down, Eagle. Listen, Tranquility Base here. The Eagle has landed.
In a sense, from this moment on, the old moon that had once been the stuff of impossible dreams completely disappeared, and a new moon of mountains and valleys and stone and dirt and possible dreams took its place.
Now, we'll get to the details of what's around here, but it looks like a collection of just about every variety of shape, angularity, granularity, but every variety of rock you could find. Fairly large number of craters of the 5 to 50 foot variety, and some ridges, small, 20, 30 feet high, I would guess, and literally thousands of little 1 and 2 foot craters around the area. There is a hill in view just about on the ground track ahead of it. Difficult to estimate, but might be a half a mile.
And throughout the world there was renewed belief, not just in American technology, but in human abilities. Thus, in the moon's sea of tranquility, a new chapter in the history of science was begun. Simultaneously, a carefully developed and planned program of scientific investigation was set in motion. There would be new information about the internal structure of the moon, the chemical composition of the rocks and soil, the dynamic processes at work, and the ages of the materials. Scientists shared a great sense of excitement. In the highest priority scientific undertaking, the astronauts collected a selection of samples of the lunar surface, the first extraterrestrial materials ever to be brought to Earth from a known context. In an experience so new, every fragment of information was of intense scientific interest.
Surface is fine and powdery. I can pick it up loosely with my toe. It does adhere in fine layers like powdered charcoal to the sole and insides of my boot. I only go in a small fraction of an inch, maybe an eighth of an inch, but I can see the footprints of my boots and the treads in the fine sandy particles.
In the centers of small craters, the astronauts discovered strange features which looked much like splattered solder or glass. The astronauts discovered rocks which had been hurled from neighboring craters, Yet they saw no impact scars in the powdery surface where the rock struck. The scars had apparently been eroded away by an unknown process. The astronauts set up an array of instruments, in effect a miniature scientific station, to return data to Earth long after the men themselves had left. One of the instruments, relatively simple in concept, was a reflecting device which would intercept a laser beam from Earth and send it back on itself. Measuring the time it took the beam to travel from the Earth to the Moon and back, scientists could calculate the distance to the Moon within a few inches. They will be able to use such precise measurements in studying the Earth. For instance, the variations in its rotation rate, the wobble of its axis, the drift of its continents. Another of the devices was a seismometer, an instrument which detects vibrations of the lunar surface. The vibrations reflect something of the nature of the internal structure and energy release of the Moon. A few months later, when Apollo 12 landed in the ocean of storms, the astronauts, given more time for scientific work on the surface, were able to enlarge on all that the Apollo 11 astronauts had accomplished. They were able to range farther, collect more and better documented samples, and set up a larger scientific station. The scientific exploration of the Moon was now well underway. The lunar materials returned to Earth were met with high excitement. More than 140 scientists from this country and abroad plunged into painstaking and intensive investigations.
We're broadening our horizons. We were never able to do that while the intense activity that took place on the surface of the Earth when it was a young planet had wiped out the record of the first billion years in its history. The Moon has now restored that missing record insofar as we can relate it to the Earth. I think it has contact with the feelings of every person, not merely with the specialist, regarding what he's doing here on the face of this planet.
Typical of the detailed efforts were studies with electron microscopes, which produced magnifications up to 1 million times and more. For some of these studies, samples were sectioned with a knife which has the sharpest edge known. It can split a hair into 10,000 sections. The scientists often felt a sense of wonder at what they saw.
This dust, which looks like gray material without interest, has exceedingly beautiful and varied forms, just from an aesthetic standpoint, as well, of course, from a scientific standpoint when you put it under the microscopes. The material is just beautiful aesthetically, and of course it's beautiful scientifically.
Among the materials, there are crystalline rocks clearly marked as igneous by bubble-like cavities and by their chemistry. They were crystallized from molten silicate material in a lunar inferno with temperatures well over 2,000 degrees Fahrenheit. There are other rocks which consist of fragments of the igneous rocks embedded in lunar soil. Called breccias, they were formed when meteorites impacted on the surface, producing such tremendous pressures that rubble and soil were welded into solid rock. Both the igneous rocks and the breccias bear clear witness to prolonged meteorite bombardment. They have been rounded as if they had been severely sandblasted, pitted where they have been struck by micrometeorites traveling at high velocity. And some coated with glass, a material which had been melted and splashed by meteorite impact. Rocks from Apollo 11 and Apollo 12 are in some ways similar, but there were important differences in chemistry, mineral composition, and texture. Further, the minerals of the Apollo 11 rocks took on their present arrangement about 3.7 billion years ago. The minerals of the Apollo 12 rocks about 3.3 or 3.4 billion years ago, an indication of two different events separated by several hundred million years. The ages were far greater than many expected. It was probably during this time, more than 3 billion years ago, that the Maria basins were filled. While the Apollo 12 rocks were generally somewhat younger, the collection did yield one unique and quite complicated rock, number 13, now famous in lunar science. Portions of rock 13 proved to be some 4.6 billion years old, very nearly the age of the solar system itself. This may be some indication of what to expect from the lunar highlands. Another type of material is the lunar soil, created, apparently, as rocks have been pulverized by bombardment. One core tube sample from the Apollo 12 landing site showed that the soil was stratified, or layered, with lighter and darker bands of material. It even seemed that one layer might have a mixture of volcanic ash. Under the microscope, it can be seen that the soil consists of tiny fragments of rocks, particles of glass, and bits of meteorites. Even the soil shows evidence of bombardment. Some of the individual grains have been so pitted, in fact, that they look almost like tiny replicas of the moon itself. In examining the lunar soils and breccias, scientists have found an abundance of products of the solar wind, the streams of particles flung off the sun. They have found, in fact, that if an ounce of lunar soil is heated to about 1800 degrees Fahrenheit at an atmospheric pressure equal to that at sea level, about 12 cubic inches of gas will be produced, primarily hydrogen and helium, directly from the sun.
It is possible, using the moon materials, to go back and trace the behavior of the sun almost back to the beginning of the solar system. The interesting part about the solar wind is that it represents the actual stuff of the sun. It's as if you had in your hands, you were able to dip into the sun and reach out and take this material and bring it back to your laboratory.
The lunar materials have also been closely searched for any trace of life, or even for any materials with organic contents. It has been a search which the scientists have so far found to be fruitless. Scientists have found the results more interesting, however, when Earth organisms have been exposed to lunar materials.
Of the variety of biological systems that we tested with the lunar material, the plants were most unique in their response. For example, the 5 jars of liverworts you see illustrated on the top gave much increased growth in the presence of lunar material. This effect was noted for ferns, a number of tissue cultures such as tobacco and corn, and certain higher plant species such as lettuce. Now, the exact reasons for this beneficial response are unknown at the present. However, it is likely that some trace mineral, or perhaps even a physical property of the lunar material, is interacting with the minerals we furnish to give a more desirable medium for plant growth. This is a very exciting discovery, and one that was totally unexpected in the tests conducted in the Lunar Receiving Laboratory.
The flood of information derived from lunar materials alone will require decades to interpret fully. In the meantime, however, still more information is flowing in from the scientific instruments set up by the astronauts. Scientists received one of their biggest surprises when the Apollo 12 seismometer told the story of how the moon vibrated when it was struck by the astronauts' abandoned lunar module.
It is as though one had struck a bell in the belfry of the church, a single blow, and found that the reverberation from it continued for 30 minutes.
The signals seem to indicate that the energy of the impact scattered greatly on one hand, but had a prolonged duration on the other. Such a combination of characteristics simply does not occur on Earth. Subsequently, signals of a similar nature were received from other impacts, both natural and man-made. After analyzing signals recorded over several months, scientists also discovered evidence of moonquakes. These occurred each time the moon passed through the point of its orbit closest to Earth, when there was maximum gravitational attraction between the two bodies. Apparently, the attraction triggered the quakes, and they were possibly of volcanic origin. So far, however, the seismometer detected no signals that would indicate events originating deep within the moon. Such events occur frequently on Earth. The upshot is that the meaning of the signals is far from understood. From other instruments, scientists are harvesting rich new information on the magnetic fields of the moon and of the Earth, the extremely thin atmosphere of the moon, the rate at which particles stream away from the sun. For a long time to come, scientists will be putting bits and pieces together, searching out the answers to a long list of questions. But already, certain parts of the whole picture are beginning to take shape. And the moon is by far a more interesting and complex body than ever anticipated. Although every current theory about the moon's origin has major flaws, it does seem probable that the major events in the formation and evolution of the moon occurred early in its history, and that relatively little has happened since then. One indication of this is the far greater frequency of craters in the highlands than in the Maria, which are themselves very old. And it means that the moon may hold records of events which have long since been obliterated from Earth by erosion. Structurally, the moon, compared with the Earth, is an extremely strong and rigid body, as it would have to be to support the great mass concentrations, mass cons, so near the surface. Scientists have seen that great heating has played a major role in shaping the moon's face. In fact, the Maria basins were filled with lava flows. They have also seen that impact has played a major role, both on a gigantic scale and on a microscopic scale. Contrary to what many expected, there has been no evidence of water. And, as most expected, there has been no trace of life, and there seems little chance of finding any. But as often happens in science, the investigations so far have raised more questions than they have provided answers. For instance, what is the interior of the moon like? What is the source of the heat that produced the lava? Was it produced in some way in the interior of the moon? Or was it generated by meteoroid impacts? What lies behind the fact that it is the side of the moon with the Maria basins that faces us on Earth? What, in detail, are the relative differences between the highlands and the Maria? And the question one always returns to, how was the moon created? In essence, the scientific investigation of the moon is one of the great intellectual adventures of our time. And a major chapter was written at the first conference for lunar science early in the year 1970.
Well, we've come an awful long way, and I think we've learned some very interesting things, but there's still an enormous amount for us to learn about the moon before we fully understand it.
When we go to the highlands, and we will go to the highlands, that they're going to be even more interesting from this point of view of the fundamental history of the solar system than the parts that we have already visited.
It is only through the understanding of the interior of this planet that we begin to start to understand some of the processes that we see on the surface of the Earth.
In fact, we are taking a step in our understanding of the solar system and the Earth that is comparable to the one taken by Galileo when he first pointed the telescope at the moon.